Okay, so this is the second tutorial lecture, and this is right after the ideal gas lecture, right? So in this tutorial's first part, we're going to be looking at questions regarding ideal gas and equations of state only, right? So let's begin. Our question says, is it reasonable to assume that at given states, the substance behave as an ideal gas? So it is basically asking us to calculate Z of given gas at given states and asking if Z is close to 1 or is it very far from 1, or basically it's trying to ask us the error in using it as an ideal gas, right? And if you remember, the error formula is 1 minus 1 upon Z. So if we find this quantity, then we will be able to tell. Or if we find even Z, and if it is like very very far from 1, we know that the closer it gets to 1, the closer it gets to ideal gas behavior. So if it is very very far from 1, then we will be able to tell what exactly is going on and if we can use it as an ideal gas or not, right? Also recall the formulas used for PR equals to P given by PC, and TR, actually let's write it up here, equals to T given by TC, because we need these to use this graph that was given in your thermo tables, right? With all that out of the way, let us begin with part A. We have O2 at 30 degrees Celsius and 3 megapascals. So our question 1, is it even a gas at this state? It could be liquefied also, it could be anything, right? So basically, first we want to verify if it is a gas or not, or if it is a superheated vapor or not, right? As we have been given pressure and temperature, we have to use P crit and T crit, and this graph. Again, this graph has come into play. This was our supercritical. This was our pre. This was our P crit line, and sorry, and this was our T crit. If you see these values from the tables, you will get the other line something like this, and your T given will be over here. So it will be a superheated vapor. I want you to do this process by yourself. If you're not clear, I want you to go back and watch the first tutorial where I have explained in detail how to do this. So yes, it is superheated, which means we can consider it as a gas and proceed with the question. However, please note that during exams, this is most often not required. This is just kind of a formality and it's trying to test you, right? So if you want to, you can do this quickly, like in the margins or whatever. But yeah, okay. So now let us calculate PR. PR equals to P given by PC. I'm writing this again and again so that it gets in your head. You will get this from table A.2, I think, equals to 0.595, and TR equals to T given by TC equals to 303 by 154.6. Again, everything in Kelvin. I have converted a given temperature into Kelvin. So TR will come out to be 1.959. Right, now let us use this graph. This can approximately be written as 0.6, right? Because it's very very close and we don't need it that accurately, right? So using this graph, first we go on the x-axis where our PR is there. 0.1, 0.2, 0 0.3, 0 0.4, 0 0.5, 0 0.6, which is very close to our given value. So we will draw this line. Right, this is our given PR line. Now we will try to look at which TR curve do we choose. Our TR came out to be 1.959, which is very close to 2. And if you see, we have the exact value given here. So if we trace this curve, get it something like this. And at the point of intersection is our given z value on the corresponding y-axis. Even if we are not able to find this accurately, we can see that in fact z is very close to 1. Z is close to 1. Therefore, we can treat it as an ideal gas. Right. So that is how we solve the question. If you didn't understand, please go back and watch it, right? Or proceed to part 2 where we will be doing the exact same thing. Let me just copy this graph one more time. Copy. Right, let's begin. In part B, we have methane. Methane is CH4 at 30 degrees Celsius, 3 megapascals. CH4 at 30 degrees Celsius, 3 megapascal. Again, we should check if it is vapor. Again, we will draw the TV graph. This is a supercritical fluid. This is PC, TC, and it will also come out to be a superheated vapor. This is our T given line, and this is our constant pressure P given line. If you see the table, your TC value should come out to be 190.4, PC should come out to be 4.60, sorry, and correspondingly we have drawn this graph and seen that it is in fact superheated. Again, do it yourself. Right, so the next step is calculating PR and TR. PR is 3 by 4.60. Again, this was P given by PC. PR will come out to be 0.652. TR is 303 in Kelvin by 190.4 equals to 1.591. T given by TC. Right, and now we will go to the graph and we will try to identify the axis, the point on the x-axis first. So we have 0.652, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and this is 0.7. So our 0.65 line will lie somewhere in between, right? So let us attempt to draw that line. Right, and now we will try to look at TR curves and which one of our TR curves we will use. Our TR came out to be 1.591, which is, we can say, to be 1.6. It's all right. So if this is the 1.5 curve and the 1.3 curve is below this, then our 1.6 curve will go something like this. No, again, a very rough estimate is required. So even if you draw some curves by hand, it's completely acceptable, right? Our 1.6 curve is something like this. And again, if we see the intersection point, The line is not straight. Why can't I draw a straight line? What's going on? My god. Does not want me to draw a straight line. Amazing. Okay, okay, okay. I'll draw it freehand. Right. As you can see, Z is again very close to 1. Not very close, but close. We can use it as an ideal gas. Right. This question was exactly the same as above. So feel free to watch back these two questions as many times as you like. Part C and part D I will not be solving fully. You'll get to know why. And part D also. First, before I tell you the solution, I want you to do the above due diligence with these two parts, and in fact, I think there's a part E as well. Yeah, with part E as well. You know, find if it is a gas. If it is a gas, use this graph and see if Z is close to 1. So, you will find that these two are not gases. They will come out to be subcooled. Will come out to be subcooled liquids. So obviously you cannot use ideal gas on them. Part E I'm leaving as your homework, and let's move on to the next question. Our next question is also about this graph, and let's move, let me just copy it. How close to ideal gas behavior is ammonia, NH3, at saturated vapor? Okay, at 100 kilopascals. So this is a part A, 100 kilopascals, and the part B is at 200 kilopascals, 2000 kilopascals. Right. So for our part A, it is given at saturated vapor. So I want you to answer where on the TV graph is our ammonia. Our ammonia is at this point. This is our P given line, which is 100 kilopascal. And this is the saturated vapor point. Remember, this is Vg. And as this is a saturated line, the corresponding temperature must be Tsat. So if we see the tables, T equals to Tsat at 100 kilopascals from this graph, and it will come out to be 239.4 Kelvin. Therefore, we are able to now calculate PR by P given upon PC, and it comes out to be 8.81 into 10 to power minus 3. Very small. Okay. And TR we are also now able to calculate because we now are able to find the T given. 239.4 by 405.5, 0.59. Can take this to be 0.6, it's okay. Now, if we see the graph, we will notice that our scale only goes down to 0.01. But if we go back here, just for the sake of argument, we'll see that anyways all of these lines are very, very convergent. So even without referring the graph, if our PR is very, very low, we can say it is close to ideal gas behavior. Why? Because beyond this 0.01 point, we can see that these lines are anyways very very convergent. So it's very close to ideal gas behavior. Part B, 2000 kilopascal and saturated vapor. Now, please note that the temperature of Tsat will not be the same because your constant pressure line has changed. Your constant pressure line has now become this because 2000 is higher than 100, right? So, this is your new Tsat. So, we want to find the new Tsat, which again we will be referring to the table. This is 2000 kilopascals, and your T will come out to be 322.37 Kelvin. Right. So our P new PR, because our given pressure has also changed, will come out to be 0.176, and our new TR, because remember if our PR changed then our Tsat also changed, which means our given temperature changed and thus TR will also change. 322.37 was 0.176. It comes out to be 0.794, which we will approximate to 0.8. Now, for this, it's going to be a bit tricky to use the table. I want you to try and use the table, but we will not be able to use it because you'll notice that the values are such that the two curves of this PR line and the TR curve, they will never actually intersect. So if we cannot use table, we can always do PV equals to ZRT. However, this is a last resort method. Always try to do it using table first. And in fact, I want you to do this process again where you identify the PR line and you identify the TR curve and you try to make them intersect. I want you to do this for this question. Pause the video and do it. After you have failed, we will try to use this equation. So in this equation, we know the P, it is 2000 kilopascals. We know the T, it is the saturation temperature, which came out to be this. We know the R from the gas because remember the R value for each gas is different. So we'll be able to find R. But what about V? How do we find V? If you see this graph very carefully, you know that our gas is at this point and the corresponding x-axis value will be our Vg. And fortunately, Vg values are available to us at the given saturation temperature and pressure. So this is why the question has given it at saturated vapor, so that we are able to find Vg for the gas. Our Vg for NH3 from the table at 2000 kilopascal will come out to be 0.06444, and if we plug all of these values into the equation, we get 2000 into 10 to the power 3, because remember pressure is in pascals, into 0.06444 equal to Z into R value will come out to be 488.2 into 322.37. So our Z comes out to be 0.8189, which is not very close to 1, but it's still close to 1. Therefore, we can assume it to be ideal gas. Again, this equation PV equals to ZRT is if all else fails. If you're not able to use the graph at all, then might as well try applying this equation, right? And with a bit of mindful thinking, we're able to see that our volume will be same as the Vg because it is at saturated vapor state, means it is at this point in the graph. So takeaway is this graph is very important and this graph is very important. Our PR and TR formulas are very important. Remembering the PV equals to ZRT equations and the units is very important. And that's pretty much it. That is all you need to solve these types of questions. In the next tutorial, we're going to be looking at the equations of state questions.